All right, so let's do a quick little review from last time. Last time we looked at two data structures. We looked at the array, and we also looked at the linked list. We're going to go ahead and look at another one at the end of class today, but I want to spend a little more time with the linked list. Let's remember a few things about the array. How is memory, or how are elements, what do they look like in memory when it comes to array? They are, was the word Anna asked me about last time, right next to each other or contiguous. So again, remember that in an array, elements, this is actually a little piece of memory that these are laid right out next to each other in memory. The issue with this was, what if there's some other, let's say like hello world next to that in memory? Well, the issue was we would have had to move all of these elements just to insert one more, maybe to another part of memory, so we move them over there or whatever, it doesn't matter. But that made the big O notation of appending big O of n. So the way we dealt with that is using this linked list. Linked list is big O of 1, so it's constant time to append something, because it doesn't matter. All you are going to do to append it, so let's say we were appending one more thing. Let's say we had one more node, we call it 4, and it has some pointer pointing to none, and all you would have to do is find the last element in the list, and then you would have to go ahead and just grab that right there. And point to the new element. So what we're going to do is, of course, because that took the same amount of steps, just to create the new node and point to it, that's why it was constant. The issue was linked list, to access it is big O of n. Does anyone remember why? Why is it big? You have to iterate or traverse through the whole linked list just to go ahead and access the nth element. So again, there was a trade-off. And what we're going to do now is we're going to actually go ahead and implement a linked list in code. If anyone ever applies for like a software engineering program job or something like that, kind of exercises involving linked lists and data structures are very common. So I want to make sure I exposed you to some of those in this course still. So if you think about what we're going to be doing is we have like two classes here. We have the actual nodes. So we have to, what we're going to need to do is we're going to have to define a class, and we'll just call it node. And we're also going to have another class, which is the actual linked list. So if you have, it's been a little bit of time since we've done anything in Python with classes, so this is a good time to review that, looking at methods, attributes, et cetera, so these are the two classes that we're going to define, and we're going to essentially build some operations to go ahead and understand this data structure called a linked list a little bit more thoroughly. Any questions before we switch over to the coding? All right, so let's do this. Okay, so the first thing we're going to need to do, remember we're not defining functions here. I said we're defining classes. So to define a class, what we'll do is just preface that with the keyword class, and then we'll go ahead and just let's call this first class node. And the node does not inherit from anything, so it's just going to have no arguments. And then remember that there's typically, when you, here, let's go ahead and just, let's say we have node 1, and we're going to instantiate it with node, and it would be nice to have basically some value. So again, remember to instantiate a class, you're just going to reference, get some sort of variable to reference it, and then you'll just go ahead and actually call the class, and that will instantiate it. But when you instantiate it, what is going to be the method that is always called? Does anyone remember? Init. Yeah, so it's a dunder method or a double underscore. So we're going to define a method. This is a special one called init, and it's going to, of course, take the keyword self, because we're going to want to be able to pass around attributes to other functions if there are functions to this class and things like that. And let's also go ahead and pass into it value. This value right here, of course, is the one that is going to be passed in when we instantiate it. Okay, so what does a node consist of? If we look at this, the node consists of the value right here, but again, we also have the second thing. Does anyone remember what this second thing was? It's a pointer or a reference to the next node in the list. In C, it was called a pointer. A lot of what I've seen when Python's doing this, they just call it the next. So we'll kind of follow that convention. Self.value is going to be equal to the value that was passed in. So remember, this is just this self.value is the attribute of the class. And this value is the one that the input binds to when it is instantiated. And then when we have an empty list, or when we have a node that's not part of the list, let's just go ahead and just have its next value set initially to none. And I kind of illustrated that right here. Node 3, if you look at it, is pointing to none because there's nothing else in that list. So honestly, that's a good start for our node class. So again, node 1, we'll just store in the value 1, and if we print it, we can just do something like this, and that is very informative, isn't it? When you print node 1, you get dunder main dunder.node object. And remember, does anyone remember from last class what this OX in front of this long string of numbers means? Yeah, it's a hexadecimal value. Remember I said memory is typically laid out and we reference memory locations using hexadecimal values? Well, if you look at this right here, this is some memory location where this node is being stored. If you remember, we illustrated that by a little grid, but yeah, there's a lot of memory in this, in whatever cloud or whatever computer we're running this code on, because if you think about it, this is 16th to the 0, 16th to the 1, 16th 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 16th to the 10th. So it's pretty high up there in memory. So yeah, 16th to 10th, very large number. But okay, does anyone remember what we would do if we wanted to basically write our own little kind of format for the printing? Was another special method, another dunder method. If you don't, that's okay. We only did it a couple times. And that's why, again, why I wanted the next project is going to be one on classes, and make sure you get a little more experience with that. So there's another dunder method called str for string, and I'm going to pass in self. I don't need to pass anything else. But what we want to go ahead and do is just return some string that it will go ahead and print in a certain way. So what I really want this to print something like, hey, I want to know that this is a node when I print this. So let's go ahead and just return the f string, and I'm going to just do node, and I'm going to go ahead and put in self.value, and I'll go ahead and it's pointing to self.next. So this is going to be very informative. So now what it'll do is it'll grab the attributes. And remember, you do need self here, because again, if you don't put self, the only method that has access to value is the init method. So we do need to precurse it. But so you can see right there, this is much more informative about like what this node actually is. It's a node with a value of 1, and it's pointing to none. All right, so that's good. That helps us at least understand a little bit better what's going on with our node class. Any questions so far? Then let's go ahead and create our linked list class. Again, it is not going to inherit from any other class. We talked about inheritance briefly. This one is just going to be its own base class. And when we go ahead and start a list, so let's go ahead and initialize it. We want to make sure we know where it starts. If you kind of think about it, one of the downsides to the linked list is that we would have to traverse the whole list to find or access certain things, but we still need to know where it starts. So what we can go ahead and do is the head of the list is initially set to none. So we'll start the list completely empty. And basically what that looks like, because let me kind of maybe write this right now, is to start things off, we're going to be looking at essentially, let's go ahead and just we'll initialize it to list, and it's just going to be pointing to none. So again, when we initialize the list, it'll be pointing to none. So let's go ahead and initialize a list down below. So I'll go ahead and comment that out. And let's go ahead and do a list. Don't use list because that would overwrite the list function. So list, and we're going to initialize it just empty. So let's go ahead and, again, you could print it if you want. Again, it's not going to give us anything very enlightening, but at least we can tell that it's initialized, that in memory, starting at this location, we have the first node, but it's not. So what we need to do is figure out a way to add nodes to the list. So one way to do that, let's go ahead and define a method. By the way, remember a method is just a function that belongs to a class. So let's go ahead and define a method called push. And what we're going to do is push some new value to the linked list. Again, remember every method does need to have its first argument as self, so it has access to the variable, so to the attribute. So this one is going to insert a new, this method will insert a new, how do I want to do this? A new node with value. To not confuse it with other values above, let's just call this one new value actually. With new value in the node. Inserts a new node with new value in the node, and I'll say at the beginning of the linked list. So we'll push it right to the beginning. As a little bit of an exercise, I'm going to give you the challenge of writing a method that will insert it at the end here in a sec. But I want to make sure, we want to go ahead and just get elements into our list. So let's think about how we're going to go ahead and do that. Well, the first thing this method should do is create a new node. So let's go ahead and create a new node, and it's going to essentially instantiate a node with whatever the value, new value. So again, that right there, you could think basically this allocates the node and puts new value as the value. All right, and if you want to just see, let's just print new node, just to kind of look at this, and we do need to actually make sure we do like list.push. And let's push 1 to it. I'm going to go ahead and just comment that out. So we're here in 27, we're instantiating a linked list. In 28, our goal is to go ahead and actually push a new node onto that list with a value 1. So what we're looking at doing so what we've done so far, let me just illustrate it here, is we've created, it's a little hard to write at this angle. Okay, so this is where we're at. That's what we've done so far. Notice it's still not on the list. And we can go ahead and print it that somewhere in memory we have node 1. So I'm going to go ahead and just get rid of that. That just confirms that. So what I'm going to now need to do is I'm pushing it to the front of the list. So my next goal is to make the new node as the head. So what I want to do here is essentially take the head of the list and point it to this one, and then I'm going to go ahead and that'll go away. So how would I do that in code? Any ideas? All right, so what you're going to do, there's two things. You're going to have to make sure that, and this is, let's see, we're going to take the new node, and what we're going to do And it's going to now, we're going to take its next and we're going to make it the head. So that right there, new node.next is now pointing to the same location as the head. So technically what it's doing, and we'll see this if we have to add more, so that's now pointing to the same thing. Oh, hold on, I need to switch. So that did, let me just write what I did here. So that's what that line does. It now points to none. And we'll see when we have to add another element why we need to do that. And now we have to go ahead and create this. Well, to do that, we're going to do the, what did I call it up here above? Self.head is now the new node. So that is basically moving our pointers around. So this points to whatever the previous head was pointing to. And then this will go ahead and make the head of the list the new node. Okay, so again, so now what this looks like is list is pointing to the first node is 1. And let's see if you want to, and just to see why we had to do that first or that middle assignment, let's say you created a new list called 2. You want that to be at the front. So this is to be a little weird. The first element of the list is to be 2. So what you'll do is you're going to point it here, and then you have to update the list to have that pointing at the head. Is that okay? Y'all understanding? I don't know. Okay, y'all look tired, but we'll keep going. Let me know if you have questions or need me to repeat anything. All right, so that's, again, you still kind of have to take my word for it that that has actually happened. But let's see if we can write a print method that actually prints the list. You know, this is just telling us where this is in memory. So let's go ahead and get a, let's go ahead and define a string method for linked list that will return the appropriate, or actually return something that tells us what's happening in the list. So let's also, so just to see, push 2. So we're gonna call that twice, and just to make sure what we're looking at this point, what are we expecting? What do we want this to do? It would be nice if it just kind of said, okay, 2 is going to be first, and then, how did I do this ahead of time? I guess it doesn't matter. Yeah, it'll work. So it would be nice if it printed something like that. Don't you agree? That we first push 1 onto the list, so that's the head. Then we push 2 on the list, and we're pushing it to the front, so 2 would go there. So that's what I want to print. That's my end goal. So how do we create that? Well, to do that, it's going to be a little bit of kind of a different paradigm of things that we've worked with before, but let's do it this way. I'm going to go ahead and create an empty string called out, and I'm going to build the string. This is what I want to output or out. And I'm going to go to the head of the list. So I'm going to create a temporary variable that points to the head of the list. All right, and now what I need to do is traverse the list. So how am I going to do that? I'm going to say while temp is not equal to none. And then you're going to, by the way, you could also have just said like while temp, because if it's not none, it'll be something. So you could also have just done like while temp, but I want to just emphasize while the head is not equal to none, what I'm going to go ahead and do is I'm going to go ahead and grab the temporary, so the value that is at the head, and again, temp is currently at the head. That's an integer, so again, if I'm appending it to a string, remember I do need to cast that to a string. So I'm going to cast the value to a string. I want to go ahead and make that fancy little arrow, since that's what linked lists are about. So I'm going to go ahead and append to my output the plus or the dash greater than or the arrow. And then there's one more thing we need to do. Anyone think they know? If you're just kind of following, we grabbed the head We printed it, we put its value inside of the value inside of the output. What do we need to do? Yeah.
Print the none.
Okay, we're eventually print the none, and again, so let me rewrite it like this right here. So we have L list, and after our second push, we're gonna have, let's do it like this. So after this, we're at L list is gonna have 2, and then it's gonna have a pointer to 1, which is then pointing to, as you pointed out here, none. So this is taken care of. So what do we need to do? We need to move to the next link, right? Because right now we just dealt with 2. So what we'll do is we're going to take temp, and we're going to then make that whatever temp is pointing to. So this right here basically traverses that pointer, and now in temp is whatever the second node was. And now we'll go ahead and print. If you want to go ahead and append none, you can. I don't think that was our goal initially. Like if you want to, this is where you would just go ahead and append none, but just a pointer floating out there. So we'll go ahead and not print. We actually want to return the output. So now let's go ahead and run this, and you can see we get a linked list like we expected. All right, any questions on that process? So that pushes it to the front. This part right here is basically us traversing the list. I'll specify since the linked list. Okay, any questions there? Yeah.
In error because it's not liking the out plus or equal to the string. It says it can't. Just give me an error.
Remember to cast it to a string. Temp.value. Don't forget to cast it. I ran into that the other day when I was coding this up. Okay, so let me go ahead and give you a little bit of exercise. So this push puts it at the front, right? Let's go ahead and define another method for this class that puts it at the end. So what we want to go ahead and do is let's go ahead and define an append method for our linked list that is it's going to take in self, and again, it's going to behave very similarly to the string or the push method as above. But what we want this one to do is just put it at the end. So this one should insert a new node at the end of the linked list. So let me give you maybe 2-3 minutes to think about that. How would you go ahead and do this? It's basically going to combine the 2 methods we've already done and the logic there. Maybe just one more thing to help you understand what we're looking to do right here is when we do list.append 3, oops, little typo there. We should have a list that goes 2, 1, 3, then none. So that's how this method should behave. Technically, I should move this down here. If anyone has a question, feel free to raise your hand. Out is an empty string. I'm building out my output because the string method expects you to return some string, and that's me just because again, if you didn't have something to start with, you can There's a couple of different ways. You could also build it as a list and then just join to the list. Here's some pseudocode up on the screen to maybe help you if you're getting some trouble. There is a corner case right here. I may encourage you to think about what the corner case would be. It won't show up in our current scenario, but there should be a little check to check for a certain corner case, and I'll bring that up if no one finds it. But there's really just three things you got to do. Create a new node, traverse the list to get to the end, because you got to find where the end of the list is, and then update the pointer to look at the new node. Let me give you maybe about another 90 seconds here. All right. By the way, so visually, this is what we're needing to do. I'm going to make another node somewhere here in memory. I'm going to create it with the value of 3. By default, it is pointing to none. So that, bless you. That's the first step. So what we're going to need to do is we're going to essentially need to go to the head of our list, and we're going to just need to traverse this. So we're going to basically look here, realize that we're still pointing to something. So now we look here. We see we're pointing to none now. So what I'm going to go ahead and do is instead of pointing to none, I'm going to point this last node in the linked list to the new node I just created, and that's it. Now there is one corner case. I'm sure, let's see if anyone was able to translate this to the code. Okay, so create a new node. So we're going to create a new node. It is going to be a node with whatever the new value that we passed into this method would be. And the corner case will come back to. So we're going to traverse the list the same way. So what we're going to do is we're going to go temp to equal self.head. So we're going to go to the head of the list. And what we're going to go ahead and do is while temp, or again you could say while temp is not equal to none, what you're going to do is you're going to go point, your temp is going to be whatever temp.next is. And maybe just to see where we're at right now, let's go ahead and just print. I wonder if, let me see, I'm curious what this will do. So let's go ahead and print temp, and I'm going to just run this to see what happens. Okay, so print temp, you can see first it was at the head, so it was, well, actually I should have printed first. So let me print temp here first. So run that, go away, run. Okay, so you can see first it printed node 2, and then it moved in the temp to temp.next, so it just printed node of 1, and node is pointing to none. So notice now it did one more movement, so you can see temp is now none. So that means it's going to exit the loop, and this is where you want to go ahead and update the pointer. What you'll go ahead and do is set temp.next. Actually, do you even want .next? No, I think you just want temp. Let's check it. So temp.next is equal to new node. Oh yeah, because you're printing the temp. So currently, so let's go ahead and run that. And that's what I thought. I think temp would just be new node now. Okay, so temp would be new node. And again, let's go ahead and actually print, hold on, temp dot, something looks off. Hold on, I messed up my, temp is not equal to none. Temp is equal to temp.next. Oh, then temp, hold on, we're missing something here. So it's none. So temp.next is now none. I think it's actually, oh yeah. Temp.next is equal to none. There we go. Because, let's try that again. So that'll do it. And now we'll, yeah, temp. And then, so but let's go through that without that now. So you can see we first look at this. Well, hold on. So let me get my head back in this. So temp is now the head. So when you print it the first time, you go ahead and print the node 2, and then of course node 2 is pointing to node 1, which is pointing to none. So you iterate, you move that. So temp is now here. And what you're going to look at now, temp.next is now none at this point. So you exit, and then you'll go ahead and set temp.next, which was pointing to none, to the new node. And now let's run this, and you can see we have the right list. Yeah.
What command did you have at the bottom?
It is, so I'm just printing the list. Is that what you were asking?
Yeah.
So I did actually use the method. All right. Anyone get it? I even messed up a little bit there, right there. And getting the hang of the pointers is a little bit of a weird idea, but essentially I wanted to go traverse the list until I found I was pointing at nothing. Once I was pointing at nothing, I want to go ahead and now point to whatever my new node was. Anyone think about what the corner case was right here? Corner cases are things that are probably like the kind of the odd man out. Realize we are making an assumption here that the list is not empty. So we do want to actually go ahead and say, if we're going to go ahead and the corner case, what we would need to do, if self.head is none, then what you would have needed to do is just said self.head is the new node. So this would have been another way, just to, it would behave like push. So that's just a catch to the corner case. The list is empty. All right, so let's go ahead and do one more method. How are we on time? Perfect. Then I want to introduce you to one more type of data structure that we'll look at next time a little bit more. But any questions there? Okay. Do you guys want this as an exercise? I think you guys could do this as an exercise. Now I'll just go ahead and do it, just so I have time to introduce to one more thing. Okay, so if you're, let's ask, what do you expect this to do? If I were to print, not lists of 2, but linked lists of 2, it's a list. What do you expect L lists of, and then using this bracket notation to do? It should go ahead and print 3. The second, again, index is 0, but I should expect this one to go ahead and basically print 3, right? But if I do this right now, it's going to just tell me linked list is not scriptable. So that's just some generic type error, and this is our own data structure. So we have to go ahead and basically say, how should this class handle access? So what we can do is define a special method called getItem. This is another dunder method. It basically gives the data structure the ability to use that bracket notation to access elements of the list. So let's go ahead and just, okay, and it's a method, so pass in self, and let's pass in n. Again, what the goal of this one is going to return the nth element in the linked list. So how are we going to do this? Well, there's a couple of different ways to go ahead and do this. You can use a for loop or a while loop. I feel like we do a lot more with for loops, so I'm going to just change it up and do a while loop. So again, remember when you have a while loop, you need to initialize some sort of counter variable outside of the while loop. And what we're going to need to do is basically traverse the list while I is less than n. So we're going to need to traverse the list while I is less than n. Of course, to traverse the list, you're going to need to get some sort of temporary variable that we're going to initially set to the head of the list. And what are we going to go ahead and do? We need to traverse the list. And again, once you get to the nth element, you'll go ahead and stop because you'll be at the item that you want to return. And you can see how accessing is big O of n now. Remember, one of the downsides here, and that's highlighted there in red, is that to access this is big O of n. So you can see here's that linear scenario. So how do we do it? Anyone think they know? Take 10, 15 seconds, 30 seconds, and see if you can maybe fill out the body of this loop and figure out what you would need to go ahead and return. I feel like class went really fast today. I don't know. Maybe just me from the looks on your faces. I guess Patrick, I did have that little question at the beginning, so that took a few minutes. I don't know, just I feel like time went way too fast. Does Professor Allman tell you all that he has that problem during class? He always tells me that. It's like, I feel like I run out of time. Let's see if anyone got this. Anyone think they got it? Kenneth, what do you think? So again, to traverse the list, you're going to basically temp is equal to temp.next. And then, okay, so then you just return temp. Let's go ahead and see what this does. And it is throwing up the issue. It's not returning this right here. So maybe you'll remember you don't want to return the whole node. You want to return value. That's still not doing it. Remember, whenever you're doing a while loop, you need to make sure you eventually give it enough information to escape the while loop. So each time through the loop, you're increment it by 1. And let's go ahead and make sure. So return I is equal to 0. Print linked list. Linked list is still giving me that. Why is that? 79 ls. Is it get item? It should be get item. Hold on. Is it get attribute? Self n. Well, and let's go ahead and see. That should be the method we use to go ahead and let's try value equal to link list of 2. Let's see if it still throws that up. That should be the method to get it. Get item, self n.
Never called a function.
Well, so let me explain where my confusion is, and I'll see if I can, and I'll need to do a quick Google search to fix it, but I'm pretty sure this was so get item is a dunder method. So I want to make sure, I might be using the wrong one because I need to check, because maybe I was doing it in 3.10. Okay, so Python magic methods, scriptable. Let me see right here. So magic or dunder, so these dunder or magic methods in Python basically implement certain functionality. So list is a class that whenever you use that bracket notation, it'll go ahead and grab the second element. So get, I wonder if it's get item, but I think I wonder if I'm using the wrong, hold on, where is my pointer now? Because I think I might have done it in 3.10. Get attribute. Get item. So self.key. This defines, raises exception to the wrong key error. And I did spell get item correctly, right? Just saying, that is, it should be a special method that implements that bit of functionality. Why is that? That's such an anticlimactic end to class. I'm just saying. Get item, I wonder if it's get attribute? No? Anyway, that's what it's supposed to do. I don't know why it's not. Tell item reverse contains missing, so return self.values of key. All right, last attempt to fix this. If not, I'll have to just look at it again and get back to you. Let's immediately just return, let's try this. Let's just immediately return 0 to see if that will do it. So run. It still is not happy about that right there. I initialized it. I initialized it as a, oh, found it. Oh gosh, such an obvious mistake. Did anyone get it working on theirs? And I realized that this is, I think there was about 4 of you who did this in project 3. Indentation, I lost track of my indentation. So notice here, append. This right here, I put as a, I indented it one too much. So now let's go ahead and run it. Now it works. So basically what I would do, it was not seeing that method because that method was nested. It's the little bugs that get you. So now this should work. There it goes. So again, it's returning 0 because that's why I hard-coded right there. So let's go ahead and correct that. So let's delete this. And we'll go ahead and try and run that again. There you go. So again, let's get rid of this printing the I. All right, so that's what I expected to do. So Kenneth, does that answer your question about what that method is doing? It essentially gives, before we implemented it, it threw out that, basically it says this object is not scriptable, but once you implement that get item, you are able to go ahead and use bracket notation to access it. Yeah, Anna.
How did you call it?
So this get item is called whenever you try to access it using bracket notation. It basically makes your object scriptable.
And then why did you assigned temp before the while loop to self-time? What is that thing?
So right here, if you were looking at this visually, it's getting you set up at the first element of the list. So it's basically saying, okay, temp is pointing here. And what you now need to do is, okay, that's not the end, so you erase that. Temp is now pointing here. Then you basically be like, oh, okay, I did it 3 times, so temp is now pointing, well, here. We would have actually, all right, let me zoom. So after we append it, this is our list. So temp basically is some variable off to the side here that we traverse through until, well, in this case, we would have done I equal to 0, then I equal to 1, then we would have stopped, and then we would have printed that value.
So you did it just to initiate using the init thing?
Yes. So yeah, I have to basically get something that allows me to move along. All right. Let me pose one question before we leave for class for the day, and then because I wanted to start this today, but I got a little hung up on a couple of things. Array. This is what where we're going to next. Searching was log of n. If it was sorted, what type of algorithm did we use to search in log of n time? It was what? It was a binary search. Very powerful. You literally cut the problem. Log n is a great running time. Searching a linked list, even if sorted, is big O of n. Why? Just traverse the list. There's no way you can just ignore the left half of the list. You have to go through the left half of the list to get to the right side of the list. So wouldn't it be nice if there was some middle ground between these? If there was some data structure that could maybe search, access, and append all in some middle ground. So maybe, again, everything has a cost. So it'd be nice if we can get search back to log n, even if that costs us somewhere else. So that's what we're going to look at next time in a binary search tree. And then we also have the best thing. There is a data structure that could search in constant time. It doesn't matter if there's 10 billion elements or 5 billion elements. It could find that element in the same amount of time. And there's a certain data structure. We've actually already seen it. We just have to kind of understand it a little bit more thoroughly. It's a very mathy data structure. So if you have questions, feel free to stick around. We'll look at binary search trees and that last mysterious data structure on Friday. Have a good day, everyone.